talk. Thank you very much for your attention.
Thank you very much for this nice talk. We have time for a few questions. So if you want to ask a question, please raise your hand. And okay, Patrick, please.
Hi, thank you, Keiichi, for this talk. So the result that we have already for discrete systems as a Markov process, is that a special case of the result that you were just presenting?
This you're saying about this result?
Yes, I guess it is also applicable to a Markov jump network. You still have the same expressions in there. You can still have the spectral gap, and I guess you can also have the deviation from the TUR.
I'm sorry. Can you say again?
So if you have a Markov network with discrete jumps, I think your result still applies.
Yes, yes. This is a general expression for applicable for general Markov jump process. Yes. And
so how does it relate to the result by Garahan and his group?
Oh yes, actually, yes. Actually, this is tighter than the original Garahan's result, actually. And
Is it tighter? Is it always tighter, or is it typically tighter?
Always tighter.
Okay, that's good to know.
Yes. So we can show explicitly about the tightness.
Okay, thank you.
Thank you also.
More questions? I can ask one in a meanwhile. So you presented this spectral gap. Do you have some intuition as to for which, depending on physical conditions, like the variation in the potential and the external force, when do you expect the spectral gap to be large or small? Meaning some kind of a simple physical intuition for this quantity.
Okay, so so mathematically, it's quite difficult to say about the value of the spectrum gap. But as I said, a small gap is quite related to the diffusion behavior. And so if the diffusion constant is very large, spectrum gaps tend to be very small. And so you're asking about the physical or mathematical situation where the spectrum gap is identified. So concerning about the mathematical condition to estimate the value of the spectrum gap, it is quite difficult to say at the moment. So actually, we considered spectrum gap for symmetrized Fokker-Planck equation. And so it's not so trivial to say about this. And we don't say about the spectrum gap for original Fokker-Planck operator, but we consider the spectrum gap for symmetrized Fokker-Planck equation. And so it's open to consider the general relation between the spectrum gap of the symmetrized Fokker-Planck equation and also for the original Fokker-Planck equation. And the physical and mathematical explanation about the value is quite difficult to say, and it's open.
Okay, thank you. More question, maybe a last question? Anyone? Okay, if not, we can take Keiichi again for a very nice talk, and we can now start with the second talk, which will be by Ivan Di Terlizzi, which will tell us about kinetic inference. Please take it.
Hello, can you see my screen? Okay, great. So hello, everyone. I'm Ivan Di Terlizzi. I currently work at the Max Planck Institute for the Physics of Complex Systems in Dresden. And I would really like to thank the organizers for inviting me to this great workshop. I really am honored. And today I'm going to talk to you about kinetic inference of entropy production. So to start, a couple of words on the framework. I'm gonna deal with the overdamped Langevin systems with a constant diffusion matrix, which is symmetric and positively defined. And in order for the second fluctuation dissipation theorem to hold, we require the temperature matrix and the mobility matrix to commute, which means that either they are both diagonal, or for the mobility matrix to be non-diagonal, we need a scalar temperature. So with this said, I would like also to give to say a couple of more words about what is the current state of methods that can be used to measure entropy production. I hope I don't bore anyone here, because this is pretty well known. But like the most basic definition of entropy production in a steady state is dissipated heat, the heat that the system is dissipating into the environment. And Sekimoto found a formula that connects this dissipated heat with the power dissipated by the forces acting on the system. And apart from all the theoretical value that this formula has, it also gives a way, in theory, to estimate entropy production by measuring the position of, let's say, a colloidal particle and the forces that are acting on this particle. But in most of the times, forces are quite difficult to estimate. At least I had my experience with red blood cells, and you have positions, but forces are really, really difficult to estimate. So like these can be a practical problem. Another way to estimate entropy production is, of course, by using the fluctuation theorem. So one can try to estimate a path probability for the forward process, a path probability for the reverse process, and then take the ratio between these two probabilities and estimate the entropy production in this way. But as you probably already know, like sampling these probability space can be really, really complicated. There are some approaches that involve the whitening on the noise, some lower bounds to these ratios. But again, even if it's possible, here we still have some other problems. Another way to exploit irreversibility is to look at irreversible currents. In particular, via the Fokker-Planck equation, one can define this mean local velocity, and then the entropy production is nothing else than the squared of these mean local velocities. And in overdamped Langevin systems, velocities are difficult to properly estimate. They are very noisy. So some techniques involve like putting a grid on space and then counting how many times a certain trace passes through some borders of this grid. And this in theory allows for thermodynamic inference, but personally, I have never seen like this method being applied to really get a number for entropy production, but rather to visualize currents and to be able to state whether the system is or not out of equilibrium. A more practical way probably to estimate entropy production is by exploiting the fluctuation dissipation theorem violation via the Harada-Sasa equation formula. In particular, you see the argument of this integral is basically zero if you are at equilibrium when response and correlation functions are linked by the fluctuation dissipation theorem. Instead, when this is broken, Harada-Sasa formula gives you a way to estimate the dissipation that led to this breaking of the FDT. And the problem here is that you really need perturbation experiments. And if you can do it, that's great. And for example, here there is a paper that I know very well, where the authors were able to measure for the first time the entropy production associated to red blood cell flickering, and this was done by estimating power spectra, so correlation functions, and response to external perturbations. But if you cannot do perturbative experiments, this is not a viable way of estimating entropy production. Finally, I'm not gonna talk a lot about this because we heard and will hear a lot about thermodynamic uncertainty relations, but like in general, we know that at short times, entropy, the TOR can be saturated, and there are ways to find optimal currents that saturate this inequality. And I know I apologize if I didn't put enough references. These are the papers that I'm more familiar with, but there have been a lot of works that exploit machine learning and all kind of techniques to infer entropy production by these short time experiments. So this said, what I'm trying to what I will talk to you about is a different approach that aims that exploits, let's say, the derivatives of correlation functions. In particular, we derived this result that connects the entropy production to the concavity of the positions correlation functions. In particular, you see as entropy production increases, here the color map is given by the entropy production, then the negative concavity of the correlation function increases. So this can be really seen as a signature of non-equilibrium, and in particular can also be used to quantify non-equilibrium. Here still we have the problem that these can be measured from the correlation function. Also, the first derivative of the correlation functions gives you the diffusive matrix, and this can also be estimated from data. But this quantity here still involves forces, so it's the same problem as we had for the formula by Sekimoto, and it cannot be used if forces cannot be estimated from data. So in order to overcome this problem, what we try to do is to express this formula instead of in terms of the true forces, which are not experimentally accessible most of the times, in terms of effective forces. And in particular, these effective forces up to a factor kBt are nothing else than the gradient of the log probability. And you see at equilibrium, this quantity here is nothing else than the derivative of the potential. So it's really a force, like maybe with a minus sign would be better actually. But the important thing is that if you access all the relevant Markovian degrees of freedom, then you can build a probability density function and eventually fit it with some kernel density estimators, and you can really get these forces. Now, by basically exploiting the connection between the real forces and the effective forces, one can rewrite this equation in terms of, again, the second derivatives of the correlation function, so the concavities, which are experimentally accessible, and the correlation matrix of these effective forces. So everything can be estimated from the data, and it requires no forces, no perturbation experiments, and also, like in terms of the statistics that you need, is totally fine with let's say with nowadays experimental setups. So in addition to like the practical relevance of these, I would like to spend a couple of words about like a more let's say theoretical interest. And indeed, what you can see is that this expression was already has already been discovered in the literature by Maes, in particular in 2007. And basically, it tells you that the entropy production is equal to 4 times the traffic, which is a very important quantity that is often found in stochastic thermodynamics. And I will tell you a little bit more about it very soon. Plus the inflow rate, which is another kinetic quantity that has been studied in the literature, in particular by Bayesi and Falasco here. And it's time symmetric, it obeys fluctuation relations, so it has a lot of interesting properties. But the important thing here is that the traffic, although it was known, it was never written in this way. And indeed, what was known about the traffic is that if you take a Langevin equation and you do Onsager-Mach loop, like very standard, then what you get is a path probability function, which is defined by an action. And the action, in total generality, can be split into a time symmetric part and a time antisymmetric part. So the time antisymmetric part is entropy production, and we find it in the fluctuation theorem, for example. So when you do path forward divided path reversed, then you only pick up the entropy, and this is why basically most of the people hear much more about entropy production rather than traffic. But the symmetric part is actually also very important. As you might imagine, it really determines the kinetics out of equilibrium. And in the literature, you find something like this. And again, it's always the same problem. So you have to estimate these drifts, which is not trivial. And also you have the derivative of a drift, which is even worse. But here we propose a new formula that has only second derivatives of correlation functions, which can be estimated from the data. So this is also part of our results. But putting all these a little bit more in practice, I would like to talk to you about this model, which is very much known in the literature. And it's a model for spontaneous oscillations in ear cell bundles. And this system is basically described by two degrees of freedom. 1 degree of freedom is the tip of the bundle, which oscillates, as you might imagine. And it's put in contact with a set of molecular motors whose center of mass can be modeled like this. So these 2 degrees of freedom are connected by this potential, and the potential contains both mechanical, which means elastical forces, and let's say chemical forces, which come from the gating dynamics of transduction channels, which are ion-based. It's kind of complicated. I'm still struggling to really understand what is going on here. But from our point of view, this is just a potential that it's conservative, and just because without this term here, which is the activity, the system is more or less on equilibrium. And I see more or less because we have an effective temperature, which is slightly bigger than T, but really it doesn't affect non-equilibrium that much. Instead, non-equilibrium really comes from this term, which is an active force, which involves feedback, as you can see. And the feedback is important because this ear cell bundle have to respond to the environment, like they are there for listening, basically. So there is active feedback. And also here there is all kind of mechanical and chemical components. So it's a really, it's a mechanosensitive system. And but again, without going too much into the detail, what's important is that this is a model that has a set of parameters that have been widely studied in the literature, and we can simulate them. So from our point of view, we simulate some traces here by varying these two quantities, which are F max, which is the maximal force that the molecular motors can exert on the bundle, and S, which is a quantity that basically tunes the calcium-mediated feedback between these transduction channels. Again, not important, but only know that these two quantities are those that tune the amount of entropy production. And in particular, you see for different set of parameters, we really get different trajectories and different probability density functions and really different entropies. So you go from there are also some that are close to 0, and you really go to thousands of kb per second. So in general, what we can do is to simulate these traces and then analyze all these traces and see whether our method to estimate entropy production works well or not. And it works in the sense that, for example, for one particular trace, we imagine of observing both degrees of freedom. Then we can calculate correlation functions. From these correlation functions, we can extract short time derivatives, first and second. So we can, from these, we can extrapolate the traffic, so the term involving the derivatives. Whereas from here, like you see, you have a long trace. Again, it's 1 million points, which is like in line with what you usually get from experiments. You build a probability density function. From this, you can reconstruct an effective force field, of which you can calculate the covariance matrix. You put all together. And as you can see, for all the set of parameters that we analyzed, the estimate of entropy production are really good, in the sense that I don't know any other works where given only the stochastic traces, you can get so good estimates, but I might be wrong. So I apologize if I'm not giving enough credit to people that have already done this. But the problem here actually is everything is very nice. I was very happy when I saw this, but problem is that most of the times experimentally you only observe 1 degree of freedom, and in particular you only observe the tip of the bundle. So what can you do in this case? What we try to exploit here is the intuition that indeed, if you only observe the concavity of these correlation functions, this might tell you something about how the system is dissipating. And again, this is under the assumption that this fluctuation dissipation theorem holds, because this is very important. If this doesn't hold, then we have some problems. But this is already enough to describe a lot of systems, by the way. Now, from this equation, from this result here, what we can see is that for non-diagonal diffusion matrix, where all the degrees of freedom are kind of mixed up together, if you only observe 1 degree of freedom, then the negative concavity of the correlation function is less than equal than the square component of the mean local velocity, which means that if this term is positive, then this term must be positive, meaning that the currents are non-zero. And if the currents are non-zero, then the system is out of equilibrium, meaning that this system, if you observe this negative concavity, it means that the system is out of equilibrium. So this might not be a lot, but as I hope I will convince you later, this is a lot, for example, in Gaussian systems. But let's postpone this for a moment. But for a diagonal matrix, what we get is actually a lower bound to entropy production. In particular, like if you observe 1 degree of freedom and you measure its traffic, then the traffic is a lower bound to the entropy production produced on that particular degree of freedom, which is less than the total entropy production, which is equal to the sum of all these local, let's say, entropy productions. So this means that in general, if we have like a set of observable degrees of freedom, let's say I, we can measure the traffic of all these degrees of freedom, and we can just pick those that are positive, we sum them together, and this is a possible lower bound to entropy production. So it's true that in general, nobody guarantees you that this is positive. But as I hope I will convince you, this, at least in some cases, it's not a big deal. So, for example, in the case of the ear cell bundle, what we have here is that for all the degrees of for all the set of parameters that we analyzed, we imagined of observing only 1 degree of freedom, which is the tip of the bundle. And the number here that you see is the amount of entropy production that we are able to measure only from that degree of freedom. And knowing that this region of the parameters is actually the one that is more relevant to biology, you can see that only by observing 1 degree of freedom, you can actually get more or less the half of the entropy that is being actually dissipated in the system. And this actually, at least in my opinion, a very good thing, because there have been some works that have been trying to estimate this dissipation from 1 single degree of freedom, and they get much less. So, like, I think this is something that proves the, let's say, the usefulness of this approach. Now, going a little bit more like into something that is more analytically solvable, it's nice to look at linear systems, because everything is solvable. We imagine for the moment that the mobility matrix is diagonal, so that things are a little bit more easy. You can calculate the mean local velocity, which gives you a condition for equilibrium. And here, basically, the source of non-equilibrium is twofold. First is like eventually a non-symmetry of the drift matrix, which means that there are non-conservative forces that are actually driving the system out of equilibrium and producing currents, or like multiple heat baths that determine like heat flows. And you can see that even if these two conditions are both met together, if they are balanced enough, then the system can still be at equilibrium. But most of the times, having these two conditions together means that the system is out of equilibrium. So for our purposes, it's important to note that the inflow rate, which is the term that we have kind of forgot in our previous discussion, is really insensible to the drivings of the non-equilibrium. So even if we cannot estimate it in the case of a partial observations, this is not a big deal, because if the entropy increases because these drivers of non-equilibrium increase, the inflow rate is not affected by it. So in a certain sense, it gives you like the sensitivity of this method. And these are some possible realization of this 2D system. But before discussing some more practical system, there is one thing that I really would like to discuss, which is the fact that even though Gaussian systems are very simple, they're absolutely not trivial from the point of view of thermodynamic inference. And this comes for this reason. So if you take a linear Langevin equation and you imagine of observing only 1 degree of freedom, then this means that you are effectively observing like an effective dynamics, which is a generalized Langevin equation. And this can also be done in a more systematic way by integrating out all non-observed degrees of freedom, hence obtaining an equation that if the system was originally at equilibrium, then the noise is correlated in such a way to obtain a fluctuation dissipation theorem of the second kind, hence ensuring equilibrium consistency. Instead, if the system was out of equilibrium, in general, you will get something that is non at equilibrium. So you have the violation of this fluctuation dissipation theorem, and the system is out of equilibrium. Point is, if you only observe this degree of freedom, then there are some works that show that if you try to infer the irreversibility of these trajectories, you always get 0. Regardless of the drivings of the non-equilibrium. So, and also that here in this other paper, the authors really go more in detail into this problem, showing that for linear systems is absolutely non-trivial to infer irreversibility, especially for single traces. So in our case, what we managed to do was to, given that we have these hypotheses on the diffusion matrix, meaning that there are no chemical reactions, so we only have diffusion and eventually some different temperatures, then it's actually possible to measure entropy production by only looking at 1 degree of freedom, or partially estimating entropy production. And in particular, you see here for some randomly chosen parameters of this 2D system, we actually get good estimates of entropy production, which are better and better as the difference in the 2 temperatures increase. But this is very system dependent, I know, but the take-home message I would say is that it's possible to have to infer non-equilibrium of Gaussian systems given the hypothesis that the diffusion matrix has this particular structure. Also, like for this system, it's very interesting to see that having a positive traffic implies that the steady state, the equilibrium solution that has that particular correlation function is not stable. So you don't have an equilibrium solution to the Fokker-Planck equation that is compatible with a positive traffic. And I think I'm running out of time, so I'll be quick. So this is another system that is interesting to discuss. It's a hierarchical system where you have a source of non-equilibrium given by this force here, which is exerted, an active force exerted on an intermediate degree of freedom y, which is then symmetrically coupled to x. So we use this system to model red blood cell flickering, and but here, just because I had the Mathematica code to do it, it was too tempting to do a little bit of simulations. And what we get here is that basically, if you are able only to look at x, it means that most of the times x, so the traffic on x will be negative because x is very far away from the source of equilibrium. Instead, y, which is more attached to the source of equilibrium, is more likely to be able to detect the non-equilibrium. Instead, if entropy production is very, very low, then we are in this region here, and both traffic components are negative, and thermodynamic inference is not possible, given that you cannot observe the active bath, which is, let's say, the most common case. So given that, I think I'm running out of time, so I wrap up with the conclusions. And I hope I convinced you that we have a novel framework to estimate entropy production directly from stochastic traces that overcomes some problems of other approaches. Of course, like our approach has limitations as well, but I mean, we have to live with that. And but one good thing for sure is that we can adapt it to partial observation. And in particular, it showed like a very good performances on a system that is biologically relevant, like the oscillations of the hair cell bundle. And for linear systems, like I think this is important. It allows non-equilibrium detection from single traces given some hypothesis on the system. So of course, like in general, if you have no hypothesis on the model, using irreversibility, it's something that is super general, but sometimes to do inference, you need specificity in a certain sense. No, it's like machine learning. I see it like this way. Instead, like if you have these hypotheses on the diffusion matrix, then you can, in theory, measure this entropy production. And usually when you have enough, you can measure it. And this said, I would like to thank you for your attention, of course, and my supervisor, Marco, who really helped me putting everything in order, and Felix for everything that I've learned from him. Thank you.